Thanks very much for the invitation, Alex, and it's a pleasure talking to you folks today. I wish I was in Texas. I visited there many, many years ago. It's been a long time, but maybe sometime when things turn around, we'll be able to do that. Okay, so today I want to talk about modeling uncertainty in learning with little data. And to start with, oops, let me get my slides going here. Just one sec. That's not happening. There we go. Okay, there we go. So can you see my cursor just to double check?
Yes, we can.
Okay, good. Okay, good. Right, so I'm going to talk about few-shot learning, and few-shot learning refers to the idea that humans can easily recognize new categories from just a single example. So this is a now famous example from a paper by Brendan Lake and colleagues from about 5 years ago, where let's say you had never seen this object shown in the top in red. That's like a segue, and then you have to pick out which of the ones below are the same object as that one. And if it's an unfamiliar object, we're still very good at it, right? Even though there's a lot of distractors and things that are similar, there's only one that really is a good match for it. So humans are very good at this, and the question is, how do we do this? How can we adapt to new classes with just a few labeled examples? And making progress in this is really an important step for really building human-like AI. And it's also very important in a lot of practical problems. So just a little anecdote on this. I had a paper on this topic a few years ago at the NeurIPS conference, and someone came up to our poster and said, and that was when Spotify was just starting, and they said, hey, we're using your few-shot algorithm to take on new users and quickly figure out their taste from just a few examples. So it's a very important practical problem for a lot of companies too. So now I want to introduce some terminology. This is a field that's filled with terms, and this is so I want to get it straight right now. So the few-shot classification, FSC, I'm going to use in this talk. We're going to define it as the task of adapting a classifier to a novel set of classes at test time, given just a few labeled examples from those novel classes. Right? So there's a lot of related terms in the literature, things like multitask learning or domain adaptation or meta learning. I'm going to stick to few-shot classification, and these are the main properties that I want to focus on. One is that the tests of the system consist of the episodes. So in an episode, you have a query example, like shown down here at the bottom, that has to be classified into one of a set of unknown classes. So all 5 of these classes, each row is a different class. These have never been seen before by the machine learning system. And you have to say, is this query part, which of the 5 classes does it belong to? And you only have a few examples, in this case, 5 examples, those are the 5 columns of each of the 5 new classes. And those are called the shots, and that's why it's few shot. But all of this is done based on a set of base classes that were used for training. And so in this case, the base classes were from the English alphabet, right? So all the handwritten characters from an English alphabet, but that's your training examples. And now we're testing on a new alphabet. In this case, it's using a very interesting data set that was developed for this particular few-shot classification. It was called the Omniglot data set. And that's an interesting one. I'll show you a little more about that here. Oh, by the way, I'd like this to be as interactive as possible. So please ask questions. I don't know if you can do it verbally, but I'll try to pay attention to the chat if the verbal one doesn't work. But happy to answer questions or take comments along the way. So this is the Omniglot set, and it's been known as MNIST transpose because MNIST is known for having a lot of different examples from just a few classes, right? The 10 handwritten digits. And now we have many, many alphabets and just a few examples of each character in each alphabet. So the alphabets would be, rather obscure ones like Aurek Besh, and there's Greek and Hebrew, lots of alphabets. And then you have different characters in the alphabet. And then for each character, you'll have 20 instances or so of different people drawing that character. And so this would be a test episode, as it's called. Remember, that's the terminology at test time. We get 20 different classes in this case, one example from each. So this would be a 20-way one-shot test episode, and you have to say, here's the query example up here, which class does it belong to? And for humans, it's not hard, right, to say it's this one. But for machines, it's not that easy. So I became interested in it partly because I thought it was a very interesting problem and a good challenge, and also because this initial paper developed a system, a clever system for doing this problem. And so in this case, Brendan Lake and colleagues, they used what's called probabilistic programming with parts, a nice alliterative title. And the parts here are these primitives. So those are these little handwritten strokes that look like this up here. And those then get put together, like you say, which ones are in a particular character and how do they connect to each other. So here you might take, this stroke, two of these guys and one of these, and put them together, and you get this this kind of proto character. And then the exemplars, the different drawings of that character, are generated by having some stochasticity. That's the probabilistic part of it. So you get these three different instances of this one character down here, a couple instances of another that's composed of other primitives, and another two examples of a third character over here. So it's a probabilistic programming approach. And I found that very interesting, but a good challenge, a challenge in the sense of saying, well, this relies on there being hand-defined or kind of, user-defined primitives in order to produce this. And the question is, can we automatically learn the underlying primitives? And I think this has been, one of the long-term challenges in machine learning. It's really about, can we learn the parts for recognizing objects in some sense? And so we developed a system where we said, well, let's try a deep learning system to do this. And after a lot of work by a grad student, Greg Koch, who's from Texas originally, we had, so the human level performance was around 96% on the Omniglot data set. And the probabilistic programming with parts was the 95.2%. And we tried a bunch of other methods. And we got to a particular version called a convolutional Siamese net, a particular version of a deep network that got up to 92%. So it didn't quite match the probabilistic programming, but it didn't require, at the same time, it didn't require any predefined parts. And so that was the goal of this work. Yeah, like I said, feel free to ask questions along the way here. So that was some early work, right? That was about 5 years ago now. And
just to clarify that point, it was
Sure.
it was using less information because the other thing had hard-coded data.
Well, the other thing had hard-coded what the primitive strokes were, right? The hard-coded these particular primitives up here. So it wasn't really data. It was just saying that, well, they looked at the characters and said, these are reasonable primitives you might define that you might want to put together to make the handwritten characters.
Okay, makes sense.
Also, sorry,
yes.
like just a quick question. Regarding the hierarchical Bayesian program learning frame, like that model, is it like similar to like conditional neural processes?
So no, well, it's quite different, right? I mean, if you look at it, I'll mention conditional neural processes in a second, but this is actually the program over here, right? It is a probabilistic programming method. So it's conditional neural processes there's kind of not really a neural net underneath it here. Conditional neural processes involve some combination of a neural net with some with latent spaces and things. I'll say something more about that, but they share some properties, but they're actually quite different.
Sounds good. Yeah, like I just like on top of my head, I remember like the tax accuracy is like quite similar. It's like also 95 point something. So I just like curious.
Yeah. Well, like these numbers now aren't that good. I mean, these numbers we can do better. Although I'll say it's not. To be fair, the 95% that people are getting now are on an easier split of the data. So this split of the data was defined by Brendan Lake, and it has a particular structure where the different test classes are different from different alphabets, and all of the tests and all things within the episode are from the same alphabet, so it's inherently a harder problem. And then there was a redefinition of the Omniglot splits that was easier, and everybody's getting 98, 99% on those now.
Oh, I see. Okay.
And Rich, you have a question in the chat.
I see that. Were the parts computed before seeing the examples in the test set? I believe they were before the ones in the test set, only using the training set, I believe. I'm not positive. Yeah. They were added before, but based on the training set, I think. We could double check that. Okay. Okay, so this is, I just want to say in general, there's been a flurry of work in this area in the last 5 years. And one of the basic problems is that you have overfitting, right? If you think of it just looking at the test set, just looking at the few examples in those 5 classes that you want to test on, you're worried about overfitting. So you don't want to train a method solely based on that. You have to use the base classes. But at the same time, you typically don't want to think about keeping around all the base class data. Sometimes you're going to use a pre-trained network, or in a lot of practical settings, you can't store that. So it's important to really adapt to all the new classes without forgetting about the base classes. There's been really remarkable results, I'd say, in the last few years, not just on Omniglot and these handwritten characters, but also using small versions of ImageNet and other data sets more recently. So I think it's a very interesting and challenging area. And there's 3 main strategies. I'm not going to go through them in detail, but I would use FAIR to define the 3 main strategies for the few-shot classification. One is called meta-learning, and that one, you learn a learning algorithm that can solve few-shot tasks that are constructed from the training set, but then you can adapt it to the test set. So there was some work by Ravi and La Rochelle, and also Chelsea Finn and colleagues done a lot of work in this area on MAML, so meta-learning method. Another kind of approach is a metric learning approach, where it's about, you can think of it as learning and embedding functions. You want to learn a mapping from the input space to some other space, such that you can compute distances, and by the distances in those classes distances in the embedding space represent the classes. And the idea is that can apply to the training set, but it also applies to the test set. So you can take novel classes in, embed novel instances in, embed them in this new space. And the idea is that instances of those novel classes should be nearby in the embedding space. Okay, so that's the metric learning approach. And what we did in our, the work I talked about earlier with the Siamese network was a version of that. There's been several other ones as well. And then the third approach is this data augmentation. So because you have very little data, you might want to generate a lot more data by, this is something that's common in machine learning, but especially common here, especially important here, because you want to apply some predefined or learned transformations to that small labeled data set that you have at test time. And it's especially interesting in few-shot classification because you want to learn how to transform, ideally, from the base classes so that you can apply it at test time. Right? So those are the 3 main types of approaches. And then, but something that's interesting to me that's happened in the last couple of years is that the exciting advances that have been made, it's a lot of 2 steps forward, 1 step back, because you have these, the ideas that kind of push this step forward and kind of hypotheses that were made, but then later found to be less valuable and unnecessary. So one example, so this is work with my group. We had something called prototypical networks. That was a version of a metric learning approach. And we said, well, we want to have a very simple network to prevent overfitting. Again, we don't have many test classes. We don't have a really complicated network that's going to fit to the base classes too much, right? Because then it won't transfer very well to the test classes. So we had built everything based on simpler networks. But then in the last couple of years, people have shown that that's not really true. If you build deep res nets, they actually do better on these tasks. A second assumption that's been common but called into question is that you want to train using the same approach that you do at test time. So this is one of the common kind of mantras from machine learning, where that, whatever your training approach should match your test time approach. And so there was a paper called Matching Nets a few years ago that suggested that, well, if you're going to do this episodic testing, where you have, let's say, 5 classes and just 5 examples of each, and that's the way you're going to test, you should do your training the same way, not train on a big batch of hundreds of classes, but divide it up into kind of mini batches where you're going to only have 5 classes and 5 examples of each, and just do that same sort of episodic training that you're going to do at test time. Okay, and they got very good results from that. Again, there's been recent results showing that standard pre-training on big batches, the standard kind of ML, mini batches, but still not doing this episodic approach does just as well. And another interesting thing is that people have worked very hard doing crafting the kind of adaptation that you want to do at test time. So in other words, you're going to do what's called meta training. You're going to train up, especially when you're doing these approaches, you want to train up some method so that that's the meta training, such that you can apply it to the support set and do a little bit of adaptation. That's to the support set. And you've learned how to do this using a meta training set. And you want to do it in a very careful way. For example, you don't want to have a lot of parameters that you're going to adapt at test time. You want to keep it very simple. So the conditional neural processes that somebody asked about, that's an example where they tried to craft something that was very simple that was going to be adapted at test time. And they threw in some other things as well. This is another version of it called CNAPS, another version of adaptation of conditional neural processes to few-shot classification, where they had some conditioning, kind of attention that was applied in a very careful way as well. And then somebody recently did an adaptation of that and said, well, all that stuff that they did actually wasn't as effective as just doing something simple on top of prototypical networks where you just add a covariance matrix and for each class, and you can adapt those parameters very quickly and do just as well. So this is just to say that there's a lot of ideas that have been floated in there to kind of try to explain good results, and it's still, kind of a wide open area for really understanding what's going on. And so I think in the field, we have to really probe beyond what the current benchmarks are. And one idea is that we want to have one way to do this is to add more structure and variety in the episodes. And so one thing I mentioned, like I said, with the original omniglot splits, there was actually this kind of structure. There was, each episode at test time had characters from within an alphabet, and that is somewhat more realistic. The idea is that, well, you're going to be in some context. You're going to be, looking at classes from within that context. We should be testing on that rather than testing on very different things. And another one is to say, well, it's also a question of what's the relationship between what you're being trained on and what you're being tested on. And often what happens is you might be trained in, so if you think of the word net hierarchy that underlies ImageNet, you might want to think about, well, we want to train on some subset of these things and then test on others. So you might train on animals and test on cars. That's very different than training on dogs and testing on cats. Right? So the question is, how fine-grained is it that you're trying to transfer from one class to another? So we developed a data set that allowed us to do that, called tiered ImageNet, that took into account the hierarchy and allowed us to have different kinds of episodes, some which tested far apart in the kind of taxonomy, and some that tested nearby. And there's been some recent work on domain shift. So let me show you what I mean by that. So one assumption is that the novel classes are going to be similar to the base classes. So here, cub is like a birds data set, where it's fine-grained classification of birds. And the results you can see in few-shot learning for a lot of methods are well above 80%, near 90%. Mini ImageNet is the small version of ImageNet, where the classes are quite different. Performances are more like, in the mid-70s. But then if we train on Mini ImageNet as the base classes and test on a very different domain, like specifically on the birds domain, you see that the performance drops. So this is really important because it's suggesting that we want to have to understand something more about the relationship between training and test classes, how they're related to each other. And there was a data set developed for this. So the idea is that, when you have this domain shift from one to the other, it's going to reduce the effectiveness of the embeddings at test time, particularly for like metric learning approaches. And this is some new work, something called the metadata set. So this is a new benchmark that allows us to evaluate across multiple data sets. So you can train up on aircraft classes and test on birds, or you can train up on traffic signs, right, and test on flowers. So it's this much larger data set that allows us to explore these questions about transfer and the relationship between classes and how important that is for some of these methods. So let me go back here. So what I want to focus on now are these questions, though, not so much about the structure in the episodes, but questions about robustness, in particular uncertainty. So robustness is really important, and that's been true, especially in general in machine learning these days, right? You want to see how sensitive are the systems to input or label noise, or perhaps to adversarial perturbations, and can we detect things that are out of distribution? And I think these are particularly relevant in the few shot setting, as I said, both because we're interested in human learning and in practical settings. This is very important. So the question is, when you have this very small amount of data at test time and are novel classes, and how robust are these systems? And now the uncertainty is a key issue as well. We don't want to think about just how well we do in terms of classification error, but how well calibrated our systems. Do they have a confidence level, or those confidences appropriate? And there's other ways of evaluating the uncertainty, the ability of the model to know what it doesn't know. This is a good recent paper that looked at some of those things. So that's what I'm going to focus on now. And I'm going to focus on these ways of capturing uncertainty, and in particular on Bayesian few-shot classification. And the Bayesian approach is, it's this natural way we can combine some prior knowledge with whatever data we get at test time. And that really fits well with this few-shot classification paradigm, because we have just a few new classes. We want to see how well we can adapt the prior to those. And now I'm going to get into some notation and some nitty-gritty, some math details. So to do that, we're going to have to define it. We have a labeled support set that is set. Each example is the examples X. There's n examples in the support set. So the support set are all of the, remember the omniglot one, we had 5 new classes and 5 examples of each. So there would have been, n would be 25 in that case. So those are all the examples that we see of the novel test classes, right? And d-dimensional. So every X, the input is d-dimensional. And the labels are going to be one-hot labels for the C different classes. All right. So in that case, there were 5 different classes. So each of the n examples is labeled as one of the 5 classes. Okay. So that's the notation. And then in the query set, we get some query. We get to see some X star. That's a query. And then we have to predict Y star. There's been a lot of interest in Bayesian few-shot classification. One approach that's common is you want to have a distribution over task-specific parameters phi, and then you share some model parameters theta across episodes. Okay, so you could have some parameters, for example, of a neural network that's being shared over episodes, and you might want to tune some task-specific parameters phi. And you want to estimate the marginal likelihood. What's the probability of the label Y for some query example given some X and theta? And you're going to integrate out over the prior over phi. Okay, so this is a standard approach. And typically, this is done by adopting variational approach and just optimizing the elbow. You assume, because of this posterior distribution, this distribution over phi given theta can be complicated. You're going to have some simpler distribution, Q of phi, your variational distribution, and you're going to try to minimize the difference between that and the true likelihood of phi given theta, and match your actual true labels as well as possible. Predict the high probability for the held out labels, right? So that's a standard approach that people have been exploring these days. But I want to take a different tack, and I want to talk about a Gaussian process approach to this problem. And so here's a one-slide introduction to Gaussian processes. Feel free to ask questions. So a Gaussian process defines a distribution over functions. So when you evaluate a function value, it's going to be Gaussian at any single point. Okay, so these would be, so you have functions. So each one of these curves is some function, let's say, and these are samples from the prior for different curves. And then the posterior would mean, well, we're going to have some observations. These are the points where the values get pinned down, because you get observed values of Y for particular X's in this case. And then where you don't have many observations, the variance grows, right? So this is the posterior samples now drawn from the posterior distribution, where the posterior is shown by this, the shaded region. And the important thing, you have a mean function. So this is the notation of Gaussian prior, which is a mean function of x. And then you have some covariance function, or the kernel function. And that's the covariance between the function evaluated at two separate points, x and x prime. All right, so that's a Gaussian process. And now we want to think about how can we apply Gaussian processes to few-shot classification. And the nice thing about Gaussian processes is that they're not reasoning over the model parameters. So what I described earlier with the elbow, the idea there in the variational distribution, that was reasoning over the parameters in a neural network. Okay, so I don't know if that was clear, but that was the idea. It was a distribution over the parameters in the network. The Gaussian process is not modeling that. Instead, it's a distribution over functions, like the simple curves I showed you before. And those are very good at capturing uncertainty. And I'll give you some examples of that in a minute, but this is the equation that's relevant for the Gaussian process. We have probability of y given x and theta. We're going to introduce some phi, and now we're going to use a Gaussian process to define the distribution of phi given x and theta, right? And then we get the probability of y given phi. So this is now our data likelihood, and these are the priors. Remember, like I showed you, the prior that we have over phi is given by, so this is like the prior in the Gaussian process here. Oops, yeah, went past it. So this is like prior samples from the Gaussian process. So now we're going to have that prior that's going to be based on the, so phi is the variable now that we're going to be having the distribution over. That's the prior, and then we have the likelihood of our observations of y given phi, right? And this requires inversion of a Gram matrix, it turns out. I'll go into that in a minute. That's the covariance matrix of all the training points. So that's daunting, and this is why people often don't use Gaussian processes, because it scales poorly with the number of training points, because the complexity is O of n cubed, and it's the number of training points, so you have to compute a covariance matrix and compute its inverse. And so it doesn't scale up very well to large data sets. There's been a lot of different approaches to do that. And so one of them is you define a set of points called the inducing points and do the Gaussian process based on, and approximate the posterior based on those inducing points. But the interesting thing is now we're doing few-shot classification. The kind of hallmark of few-shot classification is that in every episode, like at test time, we only have a few examples, right? So that's the whole idea, is that we don't have a lot of points that we're going to be considering. So the scaling problem isn't a big problem in the case of few-shot classification. But there is a remaining problem, that the Gaussian process classification, if you use a softmax likelihood, right? You have your 5 classes, you have a softmax distribution over those 5 classes. That doesn't have a Gaussian posterior. So for things to work well in a Gaussian process, both the prior and the likelihood have to be Gaussian, so that we end up with something Gaussian on the other side. It's kind of simple to work with, and analytical, nice closed forms. Otherwise, things get quite complicated. You don't have nice conjugate distributions, or all Gaussians in this case. So Gaussian GPs have been applied to few-shot regression, where the goal is to predict something continuous at test time, but it hasn't really been applied much to few-shot classification. So I'm going to describe some work that I've done with my student Jake Snell on that very recently. And this is work that's in submission to ICML, and should be out on arXiv any day now. And I should say that all the good ideas in there are really his, so he gets the credit for a lot of this work. So we'll start with binary Gaussian process classification just to build up to it. So I'm going to so imagine we have a set of examples, X, where again, we have N examples that we have C in an episode. So that's like our 25 examples that I was talking about before. Each of them has some binary label. The logits, so those are like the inputs to the sigmoid, right? If you're doing logistic regression, the logit is the input that you compute the sigmoid of. And the logits are really what the GP is going to operate over. That's the continuous value, and the GP has some mean and covariance matrix. And this kernel or Gram matrix is computed based on all pairs of points in the end. That's the kernel applied to xi and xj. All right, and that gives you your prior over your logits, right? And that was, and then the second term that you need is the likelihood. What's the probability of y given phi? And that for, you know, if you have a binary classifier, that's your standard logistic. It looks like this, right? It's the product over all the examples, e to the psi I to the yi, 1 minus e to the psi. So this is the problem. We have a binary or legit likelihood, and we have you know, this normal or Gaussian prior. So in order to deal with that, we're going to introduce an auxiliary variable, and so for this auxiliary variable, right, we have so this is our posterior over the logits, probability of psi given x and y. And like I said, we have a non-conjugate prior and likelihood. So we're going to introduce this auxiliary variable omega. And that, so here's a picture of what we're doing. We have this omega, we have psi, and given psi, we can predict y, our target, and the label, and x is observed. And so by given this posterior, this auxiliary variable, the aim is to make the distribution over psi be Gaussian, all right? So that now what we have is the probability of psi given x and y is going to be, we can integrate out the auxiliary variable, and we have probability of y given psi, which we, now we're going to see that it's Gaussian, times our prior, which was Gaussian before. So that's the aim of introducing this auxiliary variable. And how do we get there? Well, it takes a little bit of math. I'll go through it and ask questions if you'd like. So the omega has a particular form. So we chose this Pólya-gamma distribution. And this is a definition that applies to Pólya-gamma variables. And you'll see it has this nice form, which is it has a logistic kind of form over here, and then a Gaussian over here, right? E to the minus something squared. And if you take a look at this logistic and we set a to y and b to 1, that will match what we had back here, right? The product over the examples, e to the psi to the y, 1 plus e to the psi. So
to understand the point here, what exactly is the problem, and why that we're trying to solve?
Yes.
What is the difficult distribution to compute?
Right. So the difficult distribution is we want to compute this posterior over the logits, okay? And we have the probability of psi given x is normal, but the probability of y given psi is Bernoulli. So we don't get a nice conjugate form, all right? So we want to have this conjugate form. So we're trying to now introduce the auxiliary variable so that this becomes normal.
And what is high dimensional here? Sorry, I'm not, the notation is throwing me off a little bit. Which ones are the high dimensional distributions here? So P of psi given x is just Gaussian, no problem, right?
P of psi given x is Gaussian. So x are the observations. Those would be like our images.
Right.
Psi are the logits. Those would be, you know, let's say we have 5 different classes. So these are just the, you know, the inputs to those 5, the logits for those 5 classes. And y given psi is also, that's just a softmax typically.
Right. So that's all.
Right. So it's not so much the dimensionality, it's just the form.
Got it.
Okay. So this is now a binary. So we switched to a binary problem just to introduce this idea of the Pólya-gamma auxiliary variable and how it's useful in making this be conjugate, so that then we can keep everything in a nice, clean Gaussian form. Okay. Right. So and it uses this identity. So basically, with this identity, once you introduce this omega term, it turns out that these Pólya-gamma variables omega, then this is true. So we can take something that has a logistic form here on the left-hand side of this equation and turn it into something that has a normal form on the right. Okay. So when we condition on omega, we end up with a Gaussian likelihood. And you can think of it as the observations, in a sense, are just psi inverse or omega inverse times kappa, where omega is just 1 over the each of the individual omegas, right? So there's 1 per y. Okay, so now we have what we wanted. We get the probability of y given this is the posterior that we wanted is a product of a bunch of normal distributions. right? And that's what the aim was. And this is the form of that. Okay, so this is in the binary case, and our conditional posterior is Gaussian, and we can get a Gibbs sampling procedure to sample the omegas, which is this Pólya-gamma variable. Given the omega, we go back and we can sample psi, where psi has this normal, is a Gaussian. Okay, so we alternate back and forth between these two, and we can get a good posterior over y, which is our goal. All right, so again, we observe some x's, we want to have some distribution over the classes for those x's. Right? So this is for the binary case. Now we want to have multinomials. We want to have not just, you know, two classes, but several different classes. And for this, we use a kind of cool stick breaking construction. So the stick breaking construction is developed in this case for multinomials by Scott Linderman and colleagues. So that's a nice idea where we take k different logits instead of two, right? So it's not just two classes, it's k classes. And it's the product of k minus 1 binary variables here. So the multinomial over x it can be defined as the product of k minus 1 binary variables. And when you multiply them in the right way, you get the correct k, you know, probability over the k classes here. And the stick breaking idea is kind of neat. It's like the idea is that you're going to do this one by one. So you're going to start off with a stick, and then you're going to kind of stochastically choose some length less than 1 and break that stick off. You can think of it, that's the probability that's being assigned to the first class. And now the remainder classes have, you know, k1 minus whatever that probability was to fight over. Break another piece off, that's the probability for the second class. And you keep going in this recursive way, and that's why you need, you only need to do k minus 1 breaks to define the probability over all k classes. Okay, and that's kind of a nice idea. It's used a lot for multinomial variables, and it works well for. So this is an example I thought was kind of cute, where you want to predict the probability of names in New York, in the state of New York in 2012, given earlier name counts. So again, this has some nice properties in the sense that there's some smoothness properties. So you get spatially smooth, so that the similar states have similar probabilities of names. So over here, you see the probability of the name Ethan in the year 2000 was very popular in kind of the southeastern US and a little bit up here in the, oh, I don't know, whatever that is, like Montana. And so that's, and then you also have temporal smoothness. So the idea is that name preferences change smoothly over time. And this is preferences for particular names in particular places over years. So that spatial temporal smoothness assumption is important for a Gaussian process. And they can model then the name counts as multinomial draws using, so remember, the multinomial is the probability over names in New York, and you can model it that way. So what we wanted to do is use the same idea for our few-shot classification. And so we're going from binary now to multinomial. And we have our, so it's similar to what we were talking about before. We have the logits. So you can think of the logits now, we're going to use the F as our inputs to the softmax. So the softmax over classes, what probability that y equals c in the softmax, given the inputs f, the logits f, this is the standard sigmoid, right? E to the f for that particular class divided by the sum of e to the f for all the classes. The problem is that when we want to use if we want to do Pólya-gamma augmentation, it doesn't work very well in this formulation, okay? And to do that, we need to change the softmax distribution. So we considered a number of possibilities. One thing people might know about, error correcting output codes have been used a lot in machine learning for when you have lots and lots of classes. And the idea is that you want to assign, each class gets assigned binary code words, and then you have a separate binary classifier for each bit in the code. Okay, so and that could be used, we thought about doing that for multi-class. Another method that's been used in Gaussian processes for multinomials is what's called robustness, where you can say we're going to figure out what the probability is for the whatever class has the maximum probability, and assign equal probability to the others. Okay, it's distributed evenly. we chose instead something that's called the one versus each, which is a nice way of, it's kind of an approximation to the softmax, where if you take a look at the softmax distribution over here, all right, we can rewrite the softmax as something that looks a little bit more like the logistic, where the probability of y equals some class is the sum over all other classes of e to the minus the difference between those classes. And it's an approximation, so this is bigger than this term over here, where we move the, we take a product over all the other classes, and this can be rewritten as the product of a bunch of sigmoids, right? And now you can see why that might be useful, because before we had this way of using Pólya-gamma variables to convert sigmoids or logistics into normals. Okay, so that's what we're going to leverage in this case. So we have what's called the probability, the one versus each probability for a class is just the product of the sigmoid of the difference in the logits between that class and each of the other classes. Okay? And that's turns out to be a very good approximation to softmax. Okay, so just one or two more slides of these gory details, and then I'll get to some results. And just to summarize here, what we've done is we can then develop the Pólya-gamma augmentation for this multi-class Gaussian process using this one versus each construction. So our likelihood now, before we had this logistic likelihood, now for multi-class we have the one versus each likelihood, which again is a product of a bunch of sigmoids. And we can apply the same Pólya-gamma augmentation to turn that into a Gaussian likelihood. Okay, so now we have that nice form. We have a Gaussian likelihood times a Gaussian prior, so that we end up with a nice Gaussian form for the logistics of the classes that we're going to put into our, that we're used to compute the probability of our different classes. Okay, and this just follows a lot from the derivation I showed for the binary. All right. And this is just a picture to show you how this all works. Again, the graphical model is that we have these f's, which are logits, and we introduced this auxiliary variable, and this gave us an ability to have a nice posterior distribution that's Gaussian. And we have these shared parameters theta that apply not only to the logits in our support set. These are the ones, the n examples we see in an episode for few-shot classification. Remember the 5 examples of the 5 different classes. And now the queries are over here on the right side, where we see an x star, and then we compute the logits for those x stars given the shared parameters theta, and then get the probabilities over the test classes, the y stars. Okay, and these shared parameters theta are key, right? Those are the learnable parameters inside the covariance function, and those can be parameters in a deep neural network, like is used in the embedding approaches for few-shot classification, or they can be traditional kernel hyperparameters that are used in Gaussian processes. Okay, so what this is saying is that we can do Gaussian process classification, right, in this nice efficient way using Gibbs sampling of the test classes, and use this as a learning process to learn the parameters in our deep neural network. Okay, so and our learning is based on marginal likelihood. We can also do predictive likelihood. Those are 2 different objectives that have been used in this Gaussian process literature. So I'll skip through that now. So that's it, I think, for the derivation. Now I'll get into results. So the first set of results are classification on some of the few-shot benchmarks. So the question is, let's just see how this approach does. Like I said, this ends up being a way of learning a deep neural network. We can apply it at test time and just look at the accuracy at test time. So the accuracy is what's you take a look at whatever class was predicted, the highest probability of that class, and compare it to the right answer. What kind of accuracy do we get on, and we looked at 2 different data sets. One is Cub, that's the birds data set I mentioned before. And this is where you see 1 shot of each of the 5 classes at test time. And you see 5 shots of each of the 5 classes. And these are other methods that people have used, including some of the methods that, some of the current best methods, like baseline plus is one that uses a very deep ResNet and gets very good state-of-the-art results on that. And some meta learning, some metric learning approaches. This is another GP approach, but this is the GP approach I mentioned earlier that doesn't think of it as a classification problem. Instead, it casts a classification problem as a regression problem. So you can think of it as what you want to do is look at the squared error of the classes, right? That's this GPnet plus linear. And we do pretty well on this. We don't win in all cases, but we do, you know, reasonably well. This is our method, the Pólya-gamma, one versus each GP with a cosine kernel on the top. And this is marginal likelihood versus predictive likelihood. And our results are, you know, competitive on the standard few-shot classification benchmarks. But really, that's not the main focus of this work. The main focus is really trying to deal with robustness and uncertainty. So this is a question about robustness. Now we're looking at domain shift. So now we train on one domain and test on another. So we train on omniglot and test on another handwritten domain AM NIST, and we train on mini ImageNet, and we test on the birds, the cub one. And we see how well we can transfer. And you can see that we generally, again, are fairly competitive. The numbers that we get down here are in the ballpark of these other ones. So it's pretty robust, this system, to these domain shifts. Okay, but maybe more interesting is, like I said, that this is all about uncertainty. How well do we do in terms of uncertainty quantification? So one way to measure uncertainty quantification is calibration. So calibration is really saying how the aim is that your confidence of your system should match its accuracy, right? So on the x-axis in every one of these plots is the confidence of the system. So the way you can estimate the confidence of the system, one way is just saying, well, you have a softmax over classes on a given example. Look at the probability assigned to whatever has the argmax of the softmax, right? So, you know, the winning one for that particular case has a probability of 0.6. So the confidence of the system is 0.6 for that one, all right? So the confidence is on the x-axis, goes from 0 to 1 in these plots, and the y-axis is the accuracy. So calibration, this is called the expected calibration error. So the expected calibration error says, well, let's look at all of the examples that have, let's say, a confidence of 0.4. And the goal in calibration would be that what we'd like is that 40% of those examples should be correct, right? So, and if it's 0.6, 60% of them should be correct. If it's 0.8, 80% should be correct. So that's what this line is here. The diagonal is representing the case where accuracy matches confidence. In some cases, that's the goal of calibration. So I see a question, did you use stochastic variational inference? So no, this is not using variational inference. So this is using the GP inference method I was just talking about, right? So we can compare to stochastic variational inference, but that's another approach that people have used. And we're suggesting this as an alternative to stochastic variational inference using the GP, okay? And so you can see, so and what's being shown here, we have the different, two different data sets, mini ImageNet, and then the transfer from mini ImageNet to training on mini ImageNet and testing on the birds. And then the top row within each one of these pairs are methods that are kind of standard few-shot classification, not ones that are taking into account uncertainty. So these are FeatureNet and Baseline++. This is one that gets very good results on the few-shot classification, but you can see it's not very well calibrated, right? So it doesn't match the diagonal well, whereas these two matching nets and prototypical networks do turn out to be pretty well calibrated. So that was interesting, right? So that you end up getting, so these are methods that aren't directly taking into account uncertainty, yet they are fairly well calibrated. And that's true both for, and this is ours down here, these two in orange are our Pólya-gamma approach. And these are two other methods that take into account uncertainty, relation net, and the GP net that I mentioned that, you know, treats it as a linear problem, doesn't really think of it as a softmax. And you can see that ends up not being very well calibrated. All right, and the calibration results hold up both within a domain and across domains, okay? So that's the one, I think, key result that we get out of it is that the calibrate, in terms of looking at uncertainty with respect to calibration. Another one is robustness to input noise, so we can then take our examples and corrupt them. And this is common these days. People like, you know, you add Gaussian noise or impulse noise or defocus blur, and then see how well you can do at test time. And overall, you can see that, you know, the accuracy, so ours are the ones here in orange, and the accuracy is pretty high. It doesn't always win, but it's pretty high relative to the other methods. And this is the expected calibration error on these when you do add this noise. Okay, so this is now adding noise and looking at the same kind of plot we looked at before, and just looking at overall how well does it match the diagonal. So you can quantify that as expected calibration error, and you want that to be low. And you can see that defocus blur is generally something that's hard for a lot of these methods to be well calibrated to. Not really sure. I have to understand that a little bit more. Okay, so that's robustness to input noise. And then another thing that's interesting is out of episode detection. So here the idea is you want to take a train on something and then test on some example that doesn't even belong in the episode. And then you want to see, in addition to things that do belong to that set. And so you want to be able to see, not only is your system good at classifying, but also recognizing that something doesn't belong to any of those classes at all. Right? So that's a very important problem, this out of episode detection. And people haven't really looked at that at all yet. But I think it's very relevant, right? You want to be able to say, okay, I'm learning about these 5 new classes, and I'm going to be tested on those, but I also want to be able to say that something I see is really none of the above. Okay, and these are some results that we get in this kind of none of the above or out of episode. And AUC is what we're measuring here, and you can see that in general, our approaches, the ones in orange, are doing fairly well. Again, not winning throughout, but being doing quite well compared to the others. So to wrap up about the Bayesian few-shot classification, I'd say the good thing about GPs is that they give us this principled approach for reasoning about uncertainty, and we're just optimizing the marginal likelihood with the kernel parameters. So we aren't doing, as somebody mentioned there, the stochastic variational inference. We can actually just update a couple parameters at test time and do quite well. And the complexity scales in a natural way with the number of data points. Right? And we get, not only do we get competitive classification accuracy, but more interesting, I think, is we're able to get this improved uncertainty quantification. Right? Some of the open issues we want to compare to some of the approaches like the mentioned stochastic variational approaches and other methods of where they have priors over the parameters, and, whereas what we're doing is, again, priors over functions and that the GP has, right? And looking at different objectives. So this is more details, but it's interesting. The marginal and predictive likelihood give different results. They're somewhat counterintuitive here, so we're looking at that. Okay, in the last few minutes, I just want to say something about how we're extending this current paradigm. So we've already talked about some new benchmark data sets. We want to look at robustness to input label and uncertainty. But another thing is to try to move few-shot classification into more natural settings. One thing is we want to look at more unsupervised and semi-supervised work. So we had some work on this earlier. So just to give you a picture of that, we did the semi-supervised few-shot classification, where training now consists of, so this would be an example from the training set, right, where you get 3 different classes in the support set, and you have to, the queries come from those 3 classes. So this one is a dog and a piano and a bird. You also have an unlabeled set, and the idea is semi-supervised, you have this unlabeled set, and some of those unlabeled sets are like, dogs, and some of them are none of the above. Okay, so like some of them are pianos or birds, but then you have this thing over here, which is a duck, right? So it's none of the above. So it's like saying, so it is looking at this, and I think this is a very natural setting. Imagine what you're doing is you're learning about some new class or a new set of classes. But again, you have a bunch of unlabeled things that are around, and you have to say some of those unlabeled things are useful and they belong to those classes, and then some of them will belong to other classes. They're just kind of distractors. So I think this is a very difficult problem, but a very natural problem to deal with. And so we had a paper on this on meta learning for semi-supervised few-shot classification. Also, I think incremental and continual learning is really the right way to go, right? So so this idea of only testing on new classes isn't really natural in some sense. In the real world, what we do is we learn a bunch of classes, let's say, then we learn some new ones. And then what we want to be able to do is be able to recognize the old ones as well as the new ones. And this is really a continual process, right? We're continuously learning about new things and we want to retain the old ones. So that's more the question about incremental and continual learning. So I just wanted to show you, and there's a version of that which even gets more complicated, which is like a recognition in context. So I'll show you something that we're working on now. This is stuff we're just doing right now. So the idea is that you're encountering objects sequentially in some context, and the context can be useful. The context could be, you're walking through a house and now you see some new chairs you haven't seen before, and maybe some new windows or something you haven't seen before. You want to be able to recognize those, retain what you learned in the past. But the fact that you're in that context can be very useful. And the context transitions follow some distribution. So it's now you're kind of, the episodes that you might see follow some sort of temporal pattern, some temporal structure. So we're like, we're doing this thing with simulating walking through a house and then seeing new objects all the time, right? So that's some work that we're doing now and trying to learn in that case and be able to recognize objects in an environment that way, right? So, so I think I'll wrap up. So the goal of all of this, I would say, is to gain, in some sense, to gain a deeper understanding really of few-shot classification. And so these are, to me, some of the open questions that I think are most interesting in the area. So one question is, what, if anything, is really useful about episodic training? And for that one, I would say the jury is still kind of out. There's interesting, so when we said we're going to test on episodic time, and one of the mantras is you want to train in the same way that you test. And some people say, well, maybe that's not true. You just do regular pre-training. But now it turns out people are showing that you get some advantages of episodic and ways of combining training on just a few classes with training on regular whole sets of classes. And how do you combine those? And more interestingly, what is it about the episodic that is potentially useful if you're going to be tested in that way? Another question is, what should be adapted at test time? I mentioned this before. You know, there's some methods that don't just change the classifier on top, but carefully modulate what's going on in the network with forms of attention or things like that. And the question is, could you do that in a way that is going to be most useful for this task? And then a couple of my favorites are these here, right? So generative modeling is something I'm been interested in for a long time, and it seems especially important, especially kind of a ripe area for generative modeling here. Because if you only have a few training examples, you want to be able to model this novel class. Ideally, you'd be able to generate this novel class, and that should improve the recognition. So it seems like a natural place to apply generative modeling. And hierarchical Bayesian modeling is another one. That seems like another very sensible formulation of few-shot classification, where you have, you know, things that are common to sets of classes at one level, and then at different levels, right, you kind of split up. So you think of the taxonomy in ImageNet, that's the kind of thing that, and you want to build up hierarchical Bayesian modeling such that you do a good job of, you know, figuring out what is it in common about the training and test classes and what varies, right? So this is a natural way. People have pursued this. Aaron Grant and colleagues have showed that some of the meta-learning ones are naturally formulated in this way. And we're doing some theoretical work in my group trying to understand what is it about the hierarchical models can be useful, and actually looking at things like the complexity, you know, what is the sample complexity based on the relationship between the classes? And can we predict success of when we're going to get training and not? And finally, the key to all this always ends up being representational learning, of course. How can we understand or facilitate learning useful representations that will transfer to the new classes, that will enable us to do a good job of few-shot classification? And so we'll you know, kind of popular ideas like disentanglement, where you try to separate out different factors. Will that be important for few-shot classification? So that's something that people are, I think, starting to think about more. And then the last question here is really what I started with, right? So when talking about that probabilistic programming with parts, they predefine the parts. To what extent, when we've done this without predefining the parts, are we able to actually learn those underlying parts, those underlying strokes that built up those characters? And that's still, I think, an interesting open question in the area. Okay, so I think that's it for now. Thanks.
Great. Thank you, Rich. Any questions? Any further questions?
So I see there was a comment here. Continual learning requires remaining a small set of data from previous tasks, which will lead to difficulties in inverting the kernel matrix, though as it gets larger, one observes more tasks. Right, well, but so we've actually looked at continual learning where you don't have to keep around data samples from previous tasks, and you're trying to see what can you learn and retain from previous tasks without having to retain the previous examples. I agree, there's lots of methods that people try to are smart about which examples they keep from the earlier classes, so that when they learn new ones, they don't forget the old ones. They can kind of rehearse using these previously learned, or these previous examples, hopefully well-selected examples from the earlier classes. But but there are methods out there where we had a paper at NERP last year called incremental learning, where you didn't have to keep around examples from previous classes that you've learned about. And I think in the GP setting, GP could work either way. I agree that the GP could work if you keep around some examples from previous classes. The scaling properties, as you mentioned, will be hard because the scaling issues always are difficult in GPs. But again, if it's well selected and you don't need that many examples, then it can scale up in a reasonable way. So
great. I have a question actually while people maybe also thinking. I'm glad you brought up the generative modeling, and as you know, I'm very interested.
Yes.
So I guess one setting would be where you have labels for one data set, then you have a slightly different domain where you have, or a completely different domain, but let's say a slightly different domain where you have a lot of data but no labels. Right, so that would be like changing the domain, but it wouldn't be the few shot. I don't know if that would still be considered few shot if I have a lot of data unlabeled in the new domain. I guess that is that.
So typically that's, people have looked at, but to keep the terminology, that would be unsupervised few shot, because there are no labels at all at test time. But but people have considered that a bit in the few shot literature. Yes.
Right. And then what I'm interested in doing here, and we have started thinking about this problem, but we don't have any results yet, is let's say I can train a generative model for the case where I have a lot of labeled data, and I can also train a generative model for the case where I don't have a lot of labels. Can I use the generative models to leverage the few labels? Has anybody done anything like that, or would that be useful in your context? Could that be combined with your context?
Yeah. So there have been some attempts to use generative models in the way you're describing a little bit. So we did a very simple version of this a couple of years ago, where the generative model was just like a mixture of Gaussians, and you could imagine you have a mixture of Gaussians that you're learning at training time. So you use the labels there because the mixture components have labels attached to them, and at test time you again learn new mixture components, and they don't. If you do it unsupervised, they don't have any labels assigned to them, but it's still modeled as a mixture of Gaussians. And then you try to see, can you predict the labels based on that generative model? We had a workshop paper, I forget at what conference, a couple of years ago on that. It worked reasonably well, but the problem in a lot of this is that you want to see how well, if you take these benchmarks very seriously, it's difficult in generative modeling approaches so far to do very well relative to the kind of few shot benchmarks that I was showing here. There haven't been that many benchmarks that use purely unlabeled data at test time. There's been a couple papers on that. I could point you towards those. I don't think there's a well-defined benchmark on that yet, but I think there are a few people have worked on that problem.
Great, thank you. I'll follow up on that.
Sure. Yep.
Any
somebody raised their hand. I'm not sure. I can't see anything.
Yeah.
So maybe you could just say something. Yeah.
Yeah, I have a question about the scalability.
Sure.
Because you use a one versus each approach to do the multinomial case, does it scale up if we have a lot of categories? And also another question is related. So is there any advantage of using this one versus each algorithm over the stick breaking or the data augmentation scheme in the original Pólya-gamma paper for multinomial cases?
Good. So a couple questions there. So first off, so the scaling of one versus each is an issue when you have lots of classes, I would agree. I mean, typically we're doing, the hallmark of few shot classification is at a test time you're doing an episode with a confined number of classes. So 5, 10 people have looked at 20 way, even 40 way. But if you're doing 1,000 way, that's not really kind of few shot, so to speak. Now you're doing kind of pure standard ImageNet or something. And so one versus each is squared. It's quadratic in the number of classes. So it scales reasonably up to 40. If you do 1,000, it would be difficult. But I think it's okay for few shot classification, I would say, and okay for a lot of classification problems. So I should say that this one versus each method that we developed isn't really specific to few shot, but it's something that's we found very useful here. but it could work for others. And your other question was about the stick breaking. So one thing we found is that the stick breaking one, so we remember in the stick breaking, you're breaking off one piece at a time. So it's kind of order dependent. So the reason why we went away from that to the Pólya-gamma, to the augmentation method that we chose with the one versus each, was because this order dependence. We found that there was this sensitivity to the order. And even if we tried to randomize or average over many different orders, it still didn't have the right property. And that's why we looked at these other possibilities like error correcting codes or one versus each or robust max, because there is this order dependence that in Linderman's paper didn't seem to cause them problems. In ours, we had problems. There was basically what it meant was when you get down to the end of the stick, you have, it's a very low probability event that everything else has already been chosen in a sense. You have very little data left for the last bit of the stick. So this order dependence was a real problem. That's why we found that it didn't work as well in our setting.
Yeah, in the appendix of the Pólya-gamma paper, they also provide us a data augmentation scheme for the multinomial problems. So have you ever tried that?
Yeah, so we've looked at other augmentation schemes. There's, for example, there's another augmentation scheme that we've looked at that uses the probit and the conditional, the CDF of a probit as a conditional, as a augmenting variable, and that one works pretty well as well. We're currently exploring that and trying to see what are the advantages and disadvantages. So yeah, so I don't think this isn't a unique solution to the problem. It's one of other possible solutions, and in our setting so far it's worked well, but we're still exploring other potential augmentation schemes.
Okay, thank you so much.
Sure.
Great. Any other questions?
So back to your generative modeling. So one other thing I wanted to say about that is that I think, so there's some interesting work on the generative modeling that people thought about, where you can think of it as the generative modeling is very useful at test time. And so this is something that maybe ties in better maybe with cognitive science and some other methods, where you can think of it as you see something new and you're going to have generative models for new classes. And that kind of generative model is going to be trained, kind of pre-trained over old classes, but it's going to be adapted to new classes. But then really what you want to be able to do is have some classifier, like some discriminative approach at training that things get compiled into. So the idea would be that, this is good for continual learning, right? You have something where you're going to see lots of classes over time, and you're going to build up a discriminator or a classifier that's going to be very efficient for those old classes. And then for a new class, you're going to adapt the generative model, get good at those new classes, and then kind of transfer that back into your classifier. So a couple papers have looked at that. There's might be interested in a paper by Kelsey Allen, who works with Josh Tenenbaum, who had an approach like that. So I think there's some interesting hybrids between generative models and discriminative models in this setting.
I see. Okay, great. That's very interesting. I'll look into that. Okay, so I guess if there are no further questions, thank you very much, Rich. Really enjoyed the talk.
Sure.
And we will continue for another talk. Actually, we have another talk tomorrow. Thank you very much.
Okay. Bye, folks.